OCR Physics. This is the second thermal physics video, and this one is about kinetic theory. Okay, Brownian motion. What's Brownian motion? Well, 1827, Robert Brown observed the random motion of pollen grains on water. So he saw these little pollen grains and they were jiggling about on the water, and he couldn't really explain it. He thought maybe they were alive or something like that. Now, we can actually observe this if we look at smoke particles with a microscope. And hopefully you've seen this, and the smoke particles in this video, they're jiggling about. Now, why are they jiggling about? And it was not fully explained until Albert Einstein, like nearly 100 years later, explained it. And basically what's happening is that air molecules, which are invisible to us because they are tiny, 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 are banging into the smoke particles, and they are making them jiggle. Now, what does this tell us about air? Well, there must be a very, very large number of molecules because they're jiggling about like crazy. They must be moving randomly, and they must have a significant amount of momentum. I mean, the smoke particle is going to be like 1,000 times heavier than an air molecule. So the air molecules must be moving pretty quickly. And this Brownian motion is the first direct evidence that gases are made up of lots and lots of little particles moving around randomly. I mean, we take this for granted because we've been taught it in school for years and years and years, but it was quite revolutionary at the time. It's the first direct evidence that all matter is made up of little particles moving around. So, how does a gas cause pressure on the walls of its container? And looking at this, and what you should do is learn this word for word. Okay, learn this. Every second, a very large number of particles collide with the walls of the container. Look on the inside of the football there. The momentum of the particles changes, and then Newton's second law from F equals delta mv over t, and from Newton's third law, so if the wall is pushing them, they are pushing the wall, they exert a force on the wall. And then the average force divided by the area of the wall is the pressure. So if you look at my diagrams, you've got lots of particles bouncing on the inside of the wall. Force against time, it will be like raining on a roof. So, you know, lots and lots of little collisions, but then the average force divided by the area is the pressure. Learn that word for word. It's a very common question. Yeah, explain in terms of the motion of the particles how a gas exerts a pressure on the walls of its container. Also, why does the pressure increase with temperature? Because at higher temperatures, the particles have more kinetic energy, so they are moving faster. They hit the walls more often because it takes less time for them to get there and back. And the change in momentum is bigger, so the force is bigger. So, kinetic theory. What is kinetic theory? Well, it's a model. It's a model of a gas, and it's basically a gas. We think about a box full of lots and lots of little particles bouncing around on the walls of the container, and that is our model of a gas. Okay, and we can use this model to explain the properties of gases, and we can actually predict the behavior of real gases using this model. This is a model of an ideal gas. To get mathematical, that's I should say before we get mathematical, we need to make some assumptions about the gas. What assumptions? Well, learn these. Get them learned, get your flashcards done. There's a very large number of particles moving randomly. Okay, the particles are elastic spheres that have negligible volume compared to the gas. The time for a collision is much smaller than the time between the collisions, and the forces between the particles are negligible. The particles do actually bang into each other quite a lot, but in our model, that's not going to affect the pressure, okay? So learn those assumptions, get them learned. Now, using kinetic theory, we can come up with this equation here, which is PV is a third nmc squared bar. Do you need to be able to derive that? Well, the specification says that you don't. However, I've done a little summary of the derivation because there may be little bits of it that, there may be little questions you might be asked. Basically, you've got a particle which has got momentum mu, and it bangs into the wall and it comes off with minus mu. So the change in momentum is 2 mu in this elastic collision. The average force due to one particle is the change in momentum per collision divided by the time between the collisions. You multiply that by big N because there's that many particles, and then you get it back to 3 dimensions with a bit of 3-dimensional Pythagoras, and that's where the third comes from. And basically PV is a third nm c squared bar. The important thing is that this equation comes from kinetic theory. It doesn't come from any experiments, it comes from kinetic theory. So what is c squared bar? What's that then, c squared bar? Well, our gas has got n particles, where n is a ridiculously big number. And we say that the velocities of the particles are c1, c2, c3, ... up to c big N. Okay. Now, interestingly, the average velocity is 0. You know why, don't you? Because velocity is a vector. And for every particle which is moving that way, there'll be another particle which is moving that way. Yeah, so there'll be positives and negatives. The average velocity is actually 0. What would be more useful would be the average speed. So how can we get the average speed of the particle? Well, what we do is all of these C's, and as I said, half of them are positive, half of them are negative, you square them all. That gets rid of your negatives. Then you get the average value of C squared, and then you get the square root of that. So it's the root of the mean of the squares. Yes? C squared bar, which is the average of C squared, that's called the mean square speed. And that's what you see in this equation, the mean square speed. And then the square root of that is called the RMS speed, the root mean square. It's the root of the mean of the squares, the RMS speed, which is basically the average speed. So C squared bar is called the mean square speed. That's in our equation. And then the square root of that is equal to the average speed of the particles. Okay, so if the mass of each particle is little m, what would a half m c squared bar be? And that would be the average kinetic energy, wouldn't it? Talk about that a bit more. Now, have a go at this. The mass of 1 meter cubed of air at 20 degrees centigrade is 100 kilopascal, is 1.2 kilograms. Yeah. Calculate the RMS speed of the air molecules, and this is basically in the room that you're in. What's the average speed of the air molecules in the room that you're in? Might be worth guessing it before you actually work it out. If you do work it out, what you get is 500 meters per second. So the average speed of the air molecules in the room that you're in is about 500 meters per second. That's jolly fast. And it is surprising. Now, if it's surprising that the average speed is so fast, remember that Brownian motion tells us that these little air molecules must be moving very, very fast. And the fact that it's not very different from the speed of sound, that's 330 meters per second. That's not a coincidence if you think about what sound is. Bear in mind also that this is the average speed. So, half of the particles will be moving slower than that, half of them will be moving faster than that. And there will be a distribution. This graph, it's called a Maxwell-Boltzmann distribution. So basically, they don't all have the same kinetic energy, a half mc squared bar. And this is how it varies. You'll notice that from the right of the half mc squared bar, it looks very exponential, doesn't it? That's interesting. Okay, so the particles in the gas at any instant do not have the same kinetic energy, and you get this distribution here. Note also that the gas particles are continually colliding with each other elastically many times a second, a ridiculous number of collisions, yeah, every second, and they are exchanging energy. So any particular particle might be going fast and then slow and then faster and then faster and then slower and then slower many times a second. Okay, now from the ideal gas equation, do you remember PV equals NKT? Okay, in the last video. And now we have PV as a third NMC squared bar from kinetic theory. If we combine them, if we put NKT equal to a third NMC squared bar and then do a bit of rearranging, we get this. A half MC squared bar equals 3/2 KT. And that's a very interesting equation. Why? Because what have we got on the left-hand side? That's the average kinetic energy. So the average kinetic energy of the particles depends on, and it just depends on one thing, and it depends on the temperature of the gas. That is the only thing that it depends on. So the average kinetic energy of the particles is directly proportional to the temperature of the gas. So we have an objective definition of temperature. We know what temperature means. Okay. Have a go at this question. Air is a mixture of nitrogen and oxygen. Which of those particles has more kinetic energy? Which is moving faster? Okay, now the temperature is the same, so they've got the same average kinetic energy. However, the oxygen molecules will be moving slower. Why? Because they're heavier. You know, if kinetic energy is a half mc squared bar, if m is bigger, then c squared bar will be smaller. Yes, and the average speed will therefore be root 7/8 smaller. Now, back to this Maxwell-Boltzmann distribution, notice the effect of temperature here. Okay, so the temperature of a gas is a measure of the average kinetic energy. So at a higher temperature, the average kinetic energy will be bigger. And so the graph will be shifted to the right. But then as it's a distribution, it would have to be lower then. Okay, so for a low temperature and a medium temperature and a high temperature, see how the graph changes. Okay, at absolute zero, the particles would have zero kinetic energy. If it was an ideal gas, okay, they would have zero kinetic energy. And then the sum of the kinetic energies is the internal energy of the gas. So for an ideal gas, the internal energy, which is capital U, is the number of particles times this 3/2 kT, yeah, which is the average kinetic energy. If we're talking about a solid or a liquid, then there's other energies involved. There's potential energies, there's bonds between the particles. So the internal energy is the sum of all of those energies. It's the kinetic energies plus the potential energies between the particles.